Hello. This time we're going to devote some time on the concept of function composition. Now let's start with this. Let A and B be collections. Recall that a function from A to B is a relation where for each A element in the collection A, there is a unique element B in the collection B that relates to A. So we simply write this as f of A is B. We can write it because it's unique, right? Okay, what we're going to do now is introduce another function. So now let C be another collection. And G a function from B to C. Meaning that for G, the domain of G is B and the codomain of G is C. Okay? In a diagram, it looks kind of like this. We have the collection A floating here around, we have B, and we have C. Now, we have this rule that associates to each element of A an element of B. And we have this other rule that associates with each element of B exactly one element of C. We call it G. Now, imagine this has been a transporting band. No? You have A as an element of the collection capital A, and then that's going to be mapped to an element B. And then that one in turn is going to be mapped to an element C. Now, of course, the one that we associate here is exactly f of A. And the one that we associate here is exactly G of B. But put it in other terms, we can say, well, this is f of A, and G of B is C. But then that means altogether that C is nothing else but G of f of A. So what are we doing here? Well, we're constructing a new function. But remember, to declare a function, right, we have to state its domain and its codomain. And also, how is that this is going to operate on the elements of the domain, right? How is that the association is going to work? Well, this is fairly easy, because we can say that all that we have to do is that to find h of A, all that we have to do is, well, determine f of A, and then to that apply G of that. So it's going to be G of f of A. Now, this is what we call the composition of G with F. And we'll denote it by a circle, G composition with F. And when we are going to evaluate it, we'll write it explicitly, just as the way that we did it here. When you want to know what is G composed with F evaluated at A, well, that's nothing else but G of F of A. Let me provide an example so it doesn't look too dry. what I'm going to do is to declare that A, B, and C are going to be the set of real numbers. So I'll just write it. Let A be the collection of reals, B be the collection of real numbers, and also C be the collection of real numbers. Not only that, I have a function going from A to B and G from B to C with the following taking place. F of x is x squared, so f is the squaring function, and g of x is 2x plus 1. So what is that g does to its input? Well, it doubles it and then adds 1. The question is, what is g composed with f? Well, of course, it has to be a function. It is a function from A, which is the set of real numbers, to C, which is also the set of real numbers, with the following rule. When you have G composed with F and you want to evaluate it at X, well, what is that you have to do? This is G of F of X. But then you say, well, but that is nothing else but G of X squared. And then what is that G does to its input? Well, it doubles it and then adds 1. Let's see this in a diagram. It would look like this. We have A here, we have B here, and we have C here. We have our rule that associates a unique element from A to B that we call F, and we have our unique rule that associates an element of B with that of C. And let's see it as an example. We have 2. Well, that one goes to 4. And then 4 goes to 9. What will happen? Well, -1 will go to 1, and 1 will go to 3. So what's happening in general? Well, in general, A goes to A squared, and then that A squared goes to 2A squared plus 1. Now, under this particular example, let me tell you something. Note that we may also define F composed with G. Well, why is that? I'll leave that as a question for you. Is this the same as G composed with F? Well, again, another question. In this case, let me stop here, and I'll see you next time.